Hey everyone, this is Matt with Learn Everything About Design. In today's video, we're going to do part 3 of our adjustable kickstand series. Now, if you followed along with part 1 and part 2, that's a very small subset of people, but if you followed along with the first two parts of this, you'll know that we scanned the kickstand off of my KTM 450 SXF. This is an aftermarket kickstand, and it's just too long. So I've got dirt wheels, I've got dual sport wheels, and I've got supermoto wheels. And so I really needed to shorten it up for both the dual sport wheels as well as the supermoto wheels. And the idea here was to cut the kickstand, shorten it, take off about 75 millimeters of it, and then have an adjustable portion that can move to two positions, one that would be okay for the dual sport and the dirt rims, and one that would be okay for the supermoto rims if I do still have the kickstand on the bike. And so that's what we did here. I have actually designed the part, I 3D printed it, I tested it, and everything works okay. Now, obviously, with this type of process, we usually go through a couple of iterations, and this was no exception. I did make a few changes. I did modify the design slightly for a few different reasons, and we'll talk about that as we get designing. But the long and short of it is that we have a part that slides on to the cut cross section of the existing kickstand, and it offers us the ability to essentially pinch it. So there's holes that I drilled in the kickstand, and it uses an 8mm bolt. It's actually the same one that holds on the subframe and actually this kickstand to the bike. And then it pinches it in on the aluminum. So really, we get a compression here. We're not just relying on things like the 3D print strength. And in the supermoto position, the original kickstand comes all the way to the bottom. So this is basically just like an extra foot on the bottom of the part. Now I could use the super low position for the dirt rims as well. It just means that the bike leans over quite a bit. And it's probably just best to have it set up for whichever one is being currently used. And there's a fruit fly. All right. So to design this, if you want to follow along, you can go ahead and go to the description of the video and download the dataset. The dataset contains a scan body. Now, I mentioned this in the quick surface video, but I did some additional processing, and what we did was we created the end foot. And the way that this comes in, the way it was exported is a single component, but it's made up of unstitched surfaces. So the first step for us is to go through, select all of the surfaces, and then to stitch them together. This will automatically turn it into a solid body, assuming that all the edges show up as green. So once we do that, we now have a solid body version of this. Now, the way that I generally like to work with these types of designs is I'll start by pinning this component. The body is going to stay put, and I pin the component that was created. And then I want to create a copy of it. Now, there's two real ways to do this. There's copy and paste, or you can also use things like the move tool, which will create a copy of it, or copy and paste new. Now, copy and paste versus copy and paste new are two different things. If we do a copy and then go to the top of this design and do paste new, what we've done is, I'm going to capture position as well. What we've done is we've taken that original, we've created a copy of it, but the copy does not maintain any link back to the original, which means that we've got an exact duplicate. And this is important because once we go in and we actually create a 3D printed version of this, we're going to design a CNC machine version, and we're going to create a copy and paste new. So that way, all of the geometry where we've moved things that we've created, those will all still be the same, and we can break the design up, remove some features, and then configure it for CNC machining. Now, I am working with PCBWay on this. I am going to, in part 4, we're going to install final parts. For the versions I've already created, I've done some quoting. In order to get the two pieces that are needed for the CNC machine version, it's about $200 plus shipping and taxes. And then the 3D printed metal, DMLS in aluminum, is only about $48, so just under $50 for the printed metal version. Seeing how the printed plastic version works, I am going to be going with the printed metal version, but it's still important for us to understand some of the design nuances and differences. There are way too many videos out there that talk about design freedoms when you're talking about 3D printing, and that's not universally true. We have to understand the process, things like the tolerances, what geometry we can get away with, and what things we just can't. So the first step for us, now that we've got this copy and paste new, is to activate it. You'll notice that I pinned it. You don't really have to do that, but if you're worried about accidentally moving it inside of the design, then you may just want to pin it so it doesn't move anywhere. And now we've got a single body. What we're going to do is select split body. You can also use Shift and B on the keyboard. And then we're going to select the top plane or the top face of the bottom foot of this. Now this will break this up into two individual pieces. Now I can move the foot up to the correct height for what I need. Now, in reality, the distance that I have to move this is about 75 millimeters. I'm going to use nice round numbers, and that gives me enough flexibility to move the kickstand to the supermoto position, as well as still have enough material of the original kickstand left over so that I can move it to a dirt position and still have a nice bit of structure. So what we're going to do is use move copy. We're going to change the pivot point to one of these edges so that way we're moving along that axis. And then I'm going to move it up 75 millimeters. Now, when I move this up, you'll notice that the foot, because it's not perfectly aligned to the kickstand, is shifting backwards, which is totally fine because we're not actually going to use it. We're going to make our own. I just want to use it as sort of a planar reference. So we're going to say, okay, and now it's in the right location. And the next thing I'm going to do is I'm going to hide it temporarily. I also mentioned in the scanning version and the quick surface version of the videos, the part 1 and part 2, that the slot on the back is not aligned with the slot on the front. And what I mean by that is that it's actually shifted just a little bit to one side, and the bottom of the front slot is lower than the bottom of the back slot. So for our geometry, because I need to use both of those slots, I need to go up, I need to cut it as high as the back slot will allow me. And the main reason for this is because if I pull the section view down through here, using this countersunk screw, which is actually the same screw as the subframe bolts on the bike, using this, I need the material, especially since the slot on the back is offset to the left a little bit or to the rear of the vehicle. I need that to make sure that I don't have a spot where I cut through with the countersink. Now I'm using the countersink on the back side because I've got more material for thread on the front side. And that way I really just need to make sure that the bolt, or in this case, the countersunk bolt on the back side, sinks in as much as possible. The way that the factory KTM bolts work is it's an M8 by 1.25, and the countersink is actually more like a dome on the outside, which means it's not going to get hung up or caught on anything, but it's not going to sit flush either. And so because of that reason, I need to use that back slot. If I didn't have to, I could cut it wherever I wanted and just make the inside of the piece flat. Now you might be thinking you could do that and just make the walls thicker. Well, right now they're at 3 millimeters, and that gives me just enough material to make that work. I would have to make it quite a bit thicker, probably like 5, in order to work with just the flat outside material, and that's just too thick. It'd be kind of overkill, and it also makes it really bulky on the end. I want to keep it as smooth as possible. So in order to make that happen, we're going to sketch on the back side, and we're going to start with the line tool. Now, if you are new to the videos on this channel and you're just diving in at this one, I would suggest you check out part 1 and part 2, where we scanned this and then we also processed it. With these videos, I narrate as I'm going. I don't ever pre-script them. And I also always try to include design decisions along the way. So the videos tend to be a bit longer, but if that's the kind of content you're looking for, then hopefully you'll find more on the channel. All right, so we're going to split the body again. We're going to move on to using this line. With Extend Splitting Tool, whether it's a surface, a planar face, or in this case a sketch line, it will extend it out through the entire part, which is why I didn't feel the need to draw the line any bigger. Now the bottom piece here, we don't need, we can right click and remove, and then we're left with the foot, and we are left with the rest of the part. So the next step is to create the outside shape. Now, whenever we're dealing with CNC machining, 3D printing metal, or 3D printing plastic, we always have to consider our tolerances. Now, in most cases, when we're printing plastic parts, like on a desktop FDM or FFF machine, that is generally like a 0.2 millimeter offset will be a tight fit, 0.4 will be a fairly loose fit. With DMLS or 3D printed metal, where you have a powder that is laser sintered, that generally is going to be about 0.3 millimeters. That's kind of where we get to a tight fit. And so it's very similar. It's kind of right in between where we typically would see a plastic part, but I will need to use slightly larger offset numbers. I generally will do this with press pull, which is offset face after the fact. You can do it at the sketch level, but it's not really required. So what we're going to do is create a sketch. This is something that Fusion still hasn't fixed. This should be an orthographic view, but it's just never quite right if you're not sort of orthographic to the standard planes. So I find that I need to go to a true orthographic view in some of these sketches. I don't know why that is. I'm going to use my line tool, and I just want to sort of finish this off. And as I mentioned, the offset amount that we're using is going to be 3 millimeters. I don't want to chain the selection because I don't want to offset the inside stuff. So I'm going to manually go around and select this. You could change the inside edges to construction temporarily, and that would help you select the entire profile. And then we're going to pull this out, in this case, minus 3 millimeters. If you happen to use the flip option, all this does is add a negative or take the negative away from the dimension box. I wish that it was smart enough to keep a positive value. This gets a bit tricky when we're trying to link values together. All right, so we're going to use, oh, it just completely disappeared. Why did that happen? All right, so let's go ahead and I'm going to offset these 3 millimeters, and I'm going to repeat that. You can also use the space bar. I don't know why it did that. I'm going to do 3 millimeters, but then I'm going to double click on this dimension and click here so that they're linked together. And when you have an offset, you'll notice the endpoints are underdefined. As soon as I draw a line here, it should make them fully defined. Close that profile. I don't know why those disappeared. Probably had to do with the fact that the offset of this line was going in a different direction. But we're going to finish the sketch. We're going to create an extrude, which will include these inner profiles. And I'm going to bring back that little foot there. So this is going to go 2 directions. I need to go up this direction. I'm going to go a distance of 55 millimeters. That's going to get me pretty close to the end of that slot. Will give me a little bit of extra room at the top. I could go another 5 millimeters if I wanted to, but we don't really need to. And then on the other direction, we're going to go to Object, and we're going to create a new body. All right, so again, we're not using this piece right here, and so I can hide it after I'm done. And this piece I don't really need to see anymore as well. All right, so now we have the shape that we need. We need to put a hole in there. We want to center it. I'm going to center it on this front piece. Remember, the slots are slightly off. So I'm going to center it here. Fusion automatically added these extra lines, even though this is completely a planar face. You could select and delete those and then have a nice clean face. It is actually helpful for us in this case to have them there, so I'm going to leave them. It won't affect the geometry at all. If we hide the tangent edges, you'll notice that it's just a smooth face. There's nothing extra there. So it doesn't hurt us to have them. It just changes the way the view looks a little bit. But what we're going to do is we're going to sketch on that face. Again, the perspective ortho can get pretty messed up. But the way I like to approach this is I'm going to create a line from the midpoint, and I'm going to come down either perpendicular to that end or parallel to this edge. You can do whatever you want. Just make sure it's not vertical. And then hit escape and turn that to construction. I always say, like, once you get comfortable with Fusion or whatever program you're using, shortcuts are really going to save you a lot of time, whether it's X on the keyboard to turn that into construction, or whether it's using shortcuts for things like extrudes and fillets and sketch entities. They really do save you quite a bit of time. If you can't get comfortable with shortcuts, I do suggest getting comfortable with the right-click menu or the S key, and then searching for what you want. And so that can really save you a bit of time. Not everything is going to be in here. So for example, converting a line to construction is not an option in here. I don't know why. If you start to type in construction, you'll eventually find that It's just not an option in here in this toolbar, but it is right here in the sketch palette, and there is a shortcut key for it, X, so you can do that. But again, as you get comfortable, make sure that you do spend a little bit of time for that. Now I'm going to create a circle here. The hardware is 8 mm. In reality, I should make the hole a little bit bigger. I'm not actually too worried about it because I'm going to use the hole tool for the tap. So for right now, what I'm going to do is just create an 8 mm diameter as my reference. And then I want to add a dimension for this distance here. Now, this line is near vertical, which means that as I start to drag out, I won't necessarily know if it's aligned or not. So it's always a good idea to right click and make sure that it is aligned. We want to dimension the full length of the line, not the vertical dimension. And so I'm going to put that 10 mm down from the top. That'll give me enough room for the outside diameter of the countersink. And if you're not sure, you can always go ahead and put a circle that represents that outside countersink. So if you want to make sure that you are not super close to the edge there, for example, then you can put that in and just have a visual reference as a construction line. And you can also double click on these profiles and convert them to construction, which means that the only thing that we have here is that hole. So I'm going to finish the sketch. And actually, let's take a step back for a second. This is another one of those areas where shortcut keys can really speed up the workflow. So for example, if I select this, instead of hitting finish sketch, going to my tools, I can just hit E and then begin pulling that through. It'll automatically go to the extrude tool and then change it to all. And then I can hit OK, hit enter, right click and go here. And then now I've got the hole all the way through. Now for this part, what I'm actually going to do is create another sketch on this face. Again, double click the mouse. I don't know why it has so much trouble with perspective and ortho, but I want to create another circle here that's a little bit bigger. 9 mm or 10 mm will be fine. Actually, let's make it 10. And then I'm going to extrude that a distance of 3 mm. Now, the reason for this is because the countersink screw that I'm using, again, it's a factory KTM hardware, so I've got spares of them laying around. The factory hardware has a section that is not threaded. And because this is such a thin area, once we clamp this all the way down, it starts to get into where the threads would be. And so having it so that either this face is a little bit shorter or that counterbore section is there, then that'll work fine. And actually, you know what? If this is 3D printed, that's fine because it can actually be printed at that size and we don't need to get a tool to come through and drill it. If you were going to be CNC machining this, obviously you can't really create this geometry unless it was an extrusion. But if you were going to be CNC machining this, that's something that you need to consider is tool access. When we get to that part of the design, then we'll go ahead and we'll talk about it. All right, so now that that's done, the next thing is I'm going to go ahead and use the thread tool. And I want to add a thread here. Now this is going to be, again, an M8 by 0.125. For DMLS, we can 3D print the threads. It's something that we can do. Generally, you want them to be bigger than something like an M6, so an M8 would work. But DMLS 3D prints have a fairly rough texture, which means there's going to be a lot of friction. So generally, if you are going to do a modeled thread in the print, then you would want to offset the threads slightly. And again, the offset is 0.3 millimeters. It's going to be way too big for a thread. It's just not going to work. So you can make it just slightly offset, or you can leave it exactly the right size and chase it with a tap. The other thing that you could do is if this is off, it will create the appropriate size hole. And then what you can do is you can just manually tap it or have whoever's 3D printing it tap that hole. So when I 3D printed this in plastic, I printed the threads and it worked fine. And so for the final DMLS part, I'm going to print the threads and then just run a tap through it. So that way I know that the threads are clean, and that'll work out okay. On the back side, I need the countersink. I'm going to go ahead and use the hole tool with countersunk on there. I'm going to just begin to place it and snap it in that location. But the outside diameter here is going to be 16, The inside diameter is an 8 millimeter bolt. Typically that would be a little bit larger. I'm going to run it on the small side because I can always run a drill bit through. I'm looking, basically, once we get the part, we can't add material back to it, but we can, say, run a tap through the threads, or we can run a drill bit through here if we need to. And so these are things that we just kind of have to consider. With the 16 millimeter, you can kind of see where it's hitting and how much material we have. It's not a ton, but it'll be enough for what we're doing because we have more material on the outside here. And really the threads is kind of the important bit. So we're going to say, okay. All right, so now that we got those, I'm going to run a small chamfer. Actually, you know what? Take that back. This is where we need to think about the tolerances. So press pull. I am going to select all the internal faces. I don't have to select the fillets because they're going to go automatically. I'm going to go ahead and grab here. And remember I said that 0.3 is like the amount of offset that we would want. So what I'm going to do is say, actually change this to new. And we're going to set this at minus 0.15. Now, the reason I'm doing minus 0.15 is because it'll take it away from both of these faces, so that'll give us 0.3 there. It'll take it away from those sides, it'll give us a total of 0.3 there. I know that I printed this with a minus 0.1 offset for the plastic version, and it was really tight, but it worked. And so for a DMLS version, I do want to make it just a little bit looser. And again, part of that is because of surface finish, part of that is because of the DMLS tolerances. And then we want to make sure that we knock the edges off of these right here. So at least a small chamfer. Because those are external corners, it doesn't have any impact on fitting over the machined part. I can't do that to all the corners. So for example, if I put one here, then it wouldn't fit the part anymore because that's a sharp corner on the actual machined part. The other thing that we could do to help this is we could add some chamfers to the upper edges. So especially where it's going into the part, we can add a couple little chamfers here. I could select the face. It's actually probably a better way to do it. If I select the face and just do like 0.5 millimeter chamfer, that'll help ease it into the rest of the part. Again, not required. When you have a plastic part, it's a little bit easier. When you've got DMLS, a printed metal part, then adding these at the design level is pretty helpful. All right, so that part's pretty much done. The next thing we need to do is create the pad on the bottom. So I'm going to start a new sketch. And one of the problems I had originally with this kickstand, which I mentioned in the first video, is that it hit the number plate pretty bad. Like there was a lot of overlap. The original foot that went on the bottom was offset pretty far so that there was enough area for them to weld. It needed to be offset the opposite direction though for it to work. And so the way that I approach this is I'm going to use this back as a reference. So we're going to go there and we'll go here. I'm going to make both of those equal and I'm going to make both of them 16 millimeters. And then we're going to come down perpendicular, we'll come over and then we'll make those perpendicular as well. And so I want it to be flush on the backside, and then I want it to be, again, aligned. We'll do 30 millimeters, and that should be enough. And so if we extrude this, E on the keyboard, extrude all this down. It was originally done with imperial or inch bar stock, so it's actually 6.125. We are going to join these together, so I'm going to select join, and then I will apply a fillet to these corners. And so again, just kind of pick what we need, round those off. 8 looks pretty good. We are going to do another fillet here, a pretty large one, say 4. And I'll do another fillet. See if I can round that off back there. Yeah. So sometimes with geometry, especially when edges kind of lead into themselves, the order in which you create the fillets has an impact. And so this coming up the back here, that's perfectly fine for what we're doing. It's probably not ideal in all cases, especially if we were going to machine this. And I'll put a 1mm chamfer on the bottom. But there we go. So that is our 3D printed part. Now this, again, I printed it in plastic material, or at least this version of it, which is going to be, it should be pretty much exactly the same, except for the tolerances on the inside. And so, oh, and I didn't have the chamfers on the top. But one of the great things about the way that this is set up is it can be printed with this on a build plate and then built up in 3D with no supports. So that means all of the internal geometry, even the holes, they're at a slight angle, but they're built up in a way, the threads and everything, that it doesn't need any support. So it's a really good part that we can print. And so that part's done. I'm going to go ahead and save it. And then I want to design the CNC the CNC machine version. And so I'm going to go back and activate the top level. We're going to right click and copy this. And then at the top, we're going to right click and paste new. Now, once again, go ahead and capture that. Excuse me. Once again, paste new is not going to maintain a link. All right, so again, you can pin this if you want, if you're worried about moving it around. But now we've got a new version of this part. We're going to take away some features. Excuse me. So I'm going to just select the fillets. I'm going to delete all these. We'll come back and we'll add them later. And then for this extrude piece, right now it is joined together, but in reality, it's actually going to be joined to just part of this. Some of these features, like the chamfers, are probably going to be hard to machine. Again, I'm not going to be making the machined version, but I think it's important that we talk about it. So I'm going to go back into this feature, and I'm going to say new body. And if we expand this, we should see we've got this piece and this piece. There's a couple extra bodies in here that we don't need. Can remove that. And then what I want to do is split this up. But I do want to get rid of chamfers that, those will be fine. But I didn't want to get rid of that top chamfer until I can kind of get a feel for it. So what we're going to do is we're going to split that body and we're going to use this face. And so what we're left with is this piece. These two pieces are going to be joined together. So we're going to go ahead and keep them together. We're going to add that large 8mm fillet and go ahead and enter that. I'm going to say plus in here, and I'm going to add that 4mm fillet to that. And notice that this chamfer isn't something that we can really do on this part. I could go back and remove it from that original selection. So I'm going to double click on that, hold down Control, and just remove it from those. All right, so yep, so we're going to be machining basically this part from this orientation. And so this presents a couple of problems. One is this is turning into a multi-axis part pretty quickly. And two is that we really can't get down into some of these areas. Even if we could, we can't really machine those. They're going to have some sort of small radius on it. So the way to make this happen is I need to make sure that we can get a square tool in there, but also that we have some fillets, around these corners. So that basically means that the aluminum part of the kickstand is not going to be able to go all the way down to the bottom like it can on a printed version of this. And so in order to fill some of this in, I'm going to use some surface tools. We'll go to our ruled surface. We're going to select, turn off chain selection. We're going to select these planar edges, these linear edges, and we're going to go toward a direction, which will be this face. And select the face. All right, we'll say OK. I am going to create some planes on the outside here. So these are planar faces, but when we're trying to use it, in this case, I'll kind of give you some more information. What we're going to be doing is you're going to be using boundary fill. And boundary fill works with surfaces, solid bodies, and planes, construction planes. But if we select a planar face, it doesn't extend it out like it does for a split body tool, for example. All right, so we're going to go to Create Boundary Fill, select the solid, the surface, this plane, and this plane. And we're going to go to the cells. And basically we can kind of see what our result is. It's got all this stuff that's going on inside here. So I'm going to click on all these cells. You can click on the bodies as well. You don't have to click on the little check boxes if you know where the bodies are to select. It can be kind of a pain. You can also hold down the left mouse button and it'll bring up this little ghost menu. And this will let you select those check boxes too. For whatever reason, it doesn't populate. We're going to say remove tools, which means everything we use in our selection, except for the construction planes, the surfaces, the solid bodies will get removed, and the result will be what we have here. All right, so what we're left with here is basically we've filled in that bottom section. Go back to our solid tools. We filled in that bottom section, so if we're looking at this face, normal to it, we now have a face where the tool can kind of get in there and we don't have to worry about these this funky angles and the tool going down. It leaves a little bit more material there. We will need to do things like try to, fill at these corners. We can also use some tricks like select the face and hit delete. And sometimes that'll help patch those up. The other thing that we can do is this fillet. We can remove that fillet. So for example, go back into the tool and just get rid of that right there. And then just go back through the boundary fill, make sure all the cells are selected. And then we can add that 4mm fillet back at this point. And so sometimes, again, order of operations is important. But now we have to deal with these edges in here. So fillet in here and there. If we want to take, let's say, a 2mm tool in there, it's going to get pretty nasty down in this corner. It's not going to be perfect, but we cannot fillet this edge because that is where our original part is going to fit, right? So that edge it has to be sharp. We could put a tiny fillet on there, but not enough for it to make a difference for getting a tool in there. And so basically, this is going to be close, but it's not going to be a perfect representation of the part. If we try to fillet, if we turn off tangent chain and we try to fillet just that edge, you can see that it fails. We could do some manual work by sort of patching it in the corner. But again, I'm not actually going to be making the CNC version of this part, so I'm not as concerned with that. But these are things that are going to come up when you send this off to be manufactured. They're going to basically say that they can't exactly match what's in the corner. And again, for this part, it doesn't matter. What matters is that we now have a sharp corner here, which means that a large tool can come and finish off this back face and just kind of work back and forth. And then for the back piece, we basically need to split the bottom of that. And we can, again, use split body. I use this tool all the time. Select a face, have it extend, and then the piece that is at the bottom, let's see this one here, we'll just remove it. And so now these two pieces would bolt together, and we have let's go ahead and let's just take a look at this one. So this one will be much easier to manufacture. We've got a rounded corner here, so a ball nose mill or a bull, well, it couldn't be a bull nose that size. A ball end mill would be able to fit in there because the rest of the arc would come up over here. And then a small flat end or square end mill could come and make that. This could be chamfered, no problem. And then the other side, that counterbore, a countersink could be machined as well. And so this gives us a CNC'd version. We could go ahead and add some small chamfers here. It's probably not going to like that top edge. And then we can try to do a small fillet on the top. This is something that would add a lot of cost to a part. A chamfer is just going to be a single pass with a chamfer or 45-degree tool. A fillet like this is going to be several passes with a ball mill or potentially a bullnose mill, and it's just going to add a lot to the programming time. But this is the CNC'd version of our part. Let's go ahead and save that. And so, as I mentioned, thinking about several things. The function of the part, go ahead and we'll go back to the top. thinking about the function of the part, thinking about how it's going to work in practice, the fact that with a 3D printed part, we can print the geometry as is, and with a a machined part, we're going to have to make some design decisions, some adjustments. The machine part will certainly have better surface finish. The DMLS part is going to look rougher, but honestly, for this part, I'm not as concerned with it. It can be painted or coated afterwards if we need, but it's going to function better, and that's really what I'm after. And so, as I mentioned, I'm teamed up with PCBWay for this video. We are going to be using the DMLS version, so I'm going to order that one. Again, the price was about $48 versus $150 for the CNC'd front portion of the design and another $50 for the back portion of the design. And really that comes down to complexity of the design. The fact that everything's kind of at weird angles and the fact that the front piece is really leaning heavily into a multi-axis part. These are all things that are going to drive the cost up. For just purely the size and the material, it's really about a $50 part. But again, as soon as we add the complexity needed to machine that, it ends up being $150 to manufacture. So what we're going to be doing is sending this off. We're going to get it back, we'll install it, and hopefully we'll do a test to make sure everything works in the final video. If you have any questions on this or had any trouble along the way, please make sure you leave a comment. Remember that we do also sell courses. If you're looking for more design videos or you're looking for something very specific, make sure that you do check out our learneverythingaboutdesign.com website, where we do have lots of different courses for sale, and hopefully they can help you on your design journey. So once again, thanks for watching, and we'll see you in the next one.